Hey, Math and Science Academy. This is the video for the charge to mass ratio presentation. This is one that may make your brain sweat a little bit. I know it made my brain sweat a little bit as I was working on it. There's a lot to it, and we touch on a lot of topics that are pretty interesting and cool. So to start off with, this is the electromagnetic spectrum. It is made up of waves of different wavelengths. So this is like everything from long radio waves to gamma rays to X-rays, microwave, radio, TV, Wi-Fi is in there. And all of those things are caused by these waves of electricity and magnetism working together. Basically, what's going on here is that the source of these electromagnetic waves is accelerating electrons. So, like, not only are electrons like cool in so many ways, but they actually like cause all of this stuff that we use every day, all the time. So this is important. The electron's charge results in electric fields, and the electron's motion produces magnetic fields. And that is one of the things in the Google form. So you're going to want to remember that. The charge results in electric fields, and the motion of an electron results in magnetic fields. And also, electrons are part of every atom that makes up the technologies that create and receive these fields. As you know, because electrons are part of every atom. I mean, electrons are part of our world. So much so. But since they're so small, scientists have had to be creative in their efforts to learn about them. This is not something we can observe through direct observations. This is definitely an indirect observation kind of a thing here. So it's far too small to measure directly on an ordinary scale. But it is possible to find the charge to mass ratio of an electron by utilizing the forces of electric and magnetic fields acting on a moving electron. So this is the ratio that we're looking at, charge, which is represented by Q, and the charge to mass ratio, charge divided by mass. So this morning, you guys looked at the Millikan's oil drop experiment, which uses some similar principles here because we have these super tiny oil drops that are falling through this little crack in this electric plate, basically a parallel plate capacitor. And gravity is pulling it down, but then looking through a microscope, the scientists used electric force to push it back up. It's kind of like it's a charged drop of oil. So they were able to charge those plates so that it would balance right in the middle. And that's how they figured out the charge of an electron. So here is a video that goes into that some more. You can see the charge, or the charged oils kind of like suspended there. I don't want to spend the time to watch that right now. And here's another video you can use to watch that. I'm going to let you look up the links to those in the Google Classroom, but that's all explaining how that works. Essentially, we have gravity balanced out by electric force. So J.J. Thomson's experiments with the cathode ray tube came in handy for this in calculating the charge to mass ratio, because we can use these electric fields and magnetic fields to push that stream of electrons and find out how much we can deflect it and how much can be deflected by magnetism versus electric force. On the edge of the cathode ray tube is some scaling, meaning like measuring marks where they can see specifically how much it's been deflected. And this is the start of our equation here. The electric field of intensity E produces a force QE, which Q is our variable for charge. The force QE on the electrons that deflects the electrons upward. So Thomson's experiment established that electrons have a negative charge, but in order to determine the amount of their charge, both an electric field and a magnetic field were applied. So the electric field is these parallel plates here, and they're going down like this. That's where the electric field is going there. The magnets are they're perpendicular to that, so they are coming like this way. And then the beam of electrons is coming straight that way. So we have three perpendicular things going on here. So far we've seen representations of electrical fields on point charges like these. These are point charges. You can assume that the center of that electric charge is coming from the center of that of those particles there. And what you'll notice is that the electrical field lines are very curvy and they're not necessarily uniform. So to work with a uniform electric field where we have these nice parallel electric field lines, you can use what's called a parallel plate capacitor. And that makes it so that those lines are just nice and straight like that. Okay, so parallel plate capacitor makes a uniform electric field. And as we know, the cathode ray particles bent toward the positively charged plate. So then there's this question of how come if the electrical field lines are going down, why are the electrons going up? And the reason for that is just electromagnetic attraction, right? The field lines are going out, but electrons actually move against the field lines to get that positive charge, to get to the positive charge. Just like these kids running towards each other, or a kid running to their grandma. So in order to calculate the charge to mass ratio, Thomson and his associates also applied a magnetic field. So let me tell you a little bit about magnetic fields here. A couple cool facts is that if you were to cut a magnet in half, it repolarizes itself. So you're never going to have like just a north magnet over here and a south magnet over here, like you get like north and south, like you always have the north side on one side and the south side on the other side. And the other cool thing about them is that they are a closed loop. Unlike electric fields, which is kind of like reach out in all directions or reach in from all directions. Here's another cool fact about this. Electrons actually move in loops around magnetic fields, and this is going to be important later. But you can see this magnetic field, the electron is like doing helical loops around it. How cool is that? How would we know that? That is just so cool. Another thing we need to know here is that B is the universal variable for the strength of a magnetic field. I don't know why it's B, but it just is. B is the universal variable for the strength of a magnetic field. So the magnetic field in this experiment is produced by two coils called Helmholtz coils, and they're cool because they also produce a uniform magnetic field, or like uniformly straight magnetic field lines. Between the two of them, like this, you have these nice straight lines, and we're going to see that in a minute, how that is cool. Another reason that's cool is because they can be used to cancel out external magnetic fields like Earth's magnetic field, but we don't need to worry about that for this one. This is what they look like from above. You can see those parallel field lines there. So the magnetic field produced by the Helmholtz coils, first of all, let me say, so we have this beam of electrons going this way, right? Then we have the electric forces that are going up and down like this. The positive charges going down like that. And then we have the Helmholtz coils, meaning the magnetic charges that are going like this. So we have three perpendicular things going on here. So those forces are going to be pushed in different ways for each of them. They're going to feel the full force of those forces. So another way to look at this here, we have the magnetic field going this way through the coils. We have the electric parallel capacitor going straight down, and then we have the particles going this way. And these electrons are like looping around these magnetic fields. So here's where we get some really cool stuff about electricity and magnetism. Electricity and magnetism work together really well. In fact, if we were to put out a wave of electromagnetic like force here, it's made up of electrons, and the electric, like it has the same wavelength, they move in the same direction, but they move perpendicularly to each other. So here's a cool visual of that. Just super cool looking. Those waves kind of like, they are one and the same to some extent, moving in different directions while moving perpendicularly to each other in the same direction. So before we apply the magnet, the electrons make a straight line. You can see that right there like that. But then the electric field of intensity E produces a force, QE, on the electrons that deflects the electrons upward. And here's where we're starting to get into some of these equations here. So on one side we have QE, the force the electric field puts on the electrons. The force on the electrons. Then we have the magnitude of the force from the magnets. So B is the strength of the magnetic field, Q is the charge, and V is the velocity of the electron, which can be controlled by the voltage on the cathode ray tube, meaning it's going to it's going to make those electrons travel faster if you put more voltage out. So QB is the force caused by the strength of the electric field. So if you adjust the electric and magnetic fields until the cathode ray forms a straight or undeflected path, meaning you've got one pushing this way, one pushing this way, when that field is straight like it would have been before, that means those forces are equal in magnitude and opposite in direction, and the following equation is true. The force created by the magnetic field, force created by the charge of the magnetic field, and the velocity of the electron is equal to the electric field, the charge of the electric field. So I'm going to get cut off if I don't stop this video right now, so I'm going to stop right here and start it right here in a second video.